And so what that's telling us is that our v of x and y, instead of it just being g times sine, it's a sum n equals 1 to infinity of g sine n pi y over a. But the value for g could be different for all these n's. And so we have to put a little subscript n on there, because I could have g1 be a particular value, g2 is a particular value, g3. So now I have all these different values. And so I have to figure out what all of these values are. And so I'm not going to go through the entire kind of math of this. If you're interested, or if I'm not sure, if you're interested, we can talk about it later. But we go through this in math physics if you want to learn about this. But to find these GNs, we have to find the GNs by using something called Fourier's trick. And to do Fourier's trick, you multiply the left and right by sine m pi y over a, m, not n, and we integrate. And the reason that that works, the reason that it's a trick, is because sines and cosines have a particular property. Sines and cosines have this property called orthonormal. Or sorry, I shouldn't say ortho. Just forget I said the normal. They're not normal at all. Why won't you go away? Erase. Okay. What is happening here? Okay. These sorry, sines and cosines are orthogonal. So you might think of orthogonal, you might have heard orthogonal kind of like perpendicular. Orthogonal is kind of a different way to say perpendicular. This idea of something being perpendicular can be extended to functions, right? A function doesn't have a direction, but the things that functions can do sort of perpendicular actions. And so sines and cosines are orthogonal. And what that means is if I take a sine of n pi, let's use a y here. If I take a sine of n pi y over a times a sine of m pi y over a, and I integrate from 0 to 2 pi, right? Just going over one full period. What you get is two different possibilities. You get 0 if m does not equal n. And you get pi if m equals n. And so that's the idea that there's 0 most of the time. So if I have n equals 3, if I put anything else in there other than 3, it's going to give me 0. But as soon as I put a 3 and a 3, I'm going to get a pi as my answer. And so if you do this trick of multiplying and integrating, we'll end up with a formula that looks something like this. It says this gn. Now, instead of going 0 to 2 pi, I'm going 0 to a, because my my sign is going from 0 to a. So I sort of changed the limits here. So I have to put this out front because I swapped from, instead of going from 0 to 2 pi, I'm now going from 0 to a. So that's where this 2 over a comes from. And I integrate from 0 to a. And what I end up doing is I have to multiply by this constant, and I do sine of m pi y. Oops, sine n, sorry. dy. And that is a simple integral to do, right? Basically, in this case, we're just taking an integral of sine, and that's it, right? Now, I've skipped a lot of steps there. If you're interested in going through the details of how I got to this equation here from this kind of integral here, I can go through it in more detail, and maybe I'll do a separate thing, just a separate recording just showing that derivation there, but that's all done in math physics. So if you're interested in that, check that out. However, at this point, this is an integral we can do. I'm not going to bore you. You guys have integrated sine thousands of times. So I'll give you the answer. You end up with something like 2 v0 over n pi times 1 minus cosine of n pi. That's sort of the answer to this integral here. And we can actually simplify this a little bit more because we can kind of figure out what cosine of n pi does. So when n is odd, cosine of n pi is equal to -1. And when n is even, cosine of n pi is +1. Right? And so what that means is my gn is equal to, sort of in two different setups, it's equal to 0 if n is even, right? Because I get 1 minus 1. And it's equal to, oops, I don't know why that keeps happening. 4 v0 over n pi if n is odd. So sorry, I know I went over 2 minutes here, but let's just write down the final full answer here. That my final v of x and y is equal to 4 v0 over pi. That's sort of all these constants out front. And then I have a big old sum, n equals 1, 3, 5, et cetera, so only the odd up to infinity of 1 over n e to the minus n pi over a sine n pi y over a. Sorry, that was a terrible box. So the point here being that even though we have we've made some assumptions and it got complicated in the end there because of that Fourier's trick. But again, that Fourier's trick just boils down to doing one integral. We now have this solution here. So you could plug this in. It's not very obvious to see what that looks like, but you could plug that into like MATLAB or some kind of graphing program, and you'll see that it would give you sort of a plot that would look like you would expect, this sort of potential to look like. It would drop off to 0. It would be 0 at the plates and v0 at the green spot there. Okay. All right. So that's all I got. So two different big techniques is method of images, which means replace it with a simpler problem. Separation of variables, which means you make an assumption about solving the differential equation and then plug away at the boundary conditions. Oftentimes you have to do this kind of Fourier's trick summation thing in the end. But the important part is that first bit where we did X and Y sort of separated there.